I've drawn a nuclear reactor for you, and I'm going to just explain some of the principles of it and how it works. So a nuclear reactor will be within a containment structure, and that is there in case of any accidents. That's there in case there's anything goes wrong. So that would be very, very thick concrete. So most of the all of the material that could be radioactive is housed within this containment structure, which is made of thick concrete. The thick concrete is there to absorb any gamma radiation to ensure that anyone who's working at the nuclear power station is kept safe from that. So within the power station itself, you've got the reactor core. So this would be the reactor core, and within the reactor core there are a number of things. There are the fuel rods, which will usually contain the uranium fuel. There are control rods, which I'll explain in a second. There will be the moderator, which again I'll explain in a second, and there will be some coolant. Okay, so the fuel rods, fairly self-explanatory. The fuel rods contain the fissile material. So fissile is the adjective you'd use to describe nuclei which can fission. So the fissile material usually used is uranium-235. So there are fuel rods within the reactor which can be replaced when the uranium-235 that's in there drops down to a low enough level that there isn't enough left. So they would periodically replace fuel rods. The control rods have a slightly different role. And last lesson you looked at the chain reaction that causes a nuclear explosion. Well, the control rods are there to allow control of the rate of chain reaction. So that's control of rate of chain reaction. And they are made from a material which will absorb neutrons. So the neutrons are crucial. The neutrons are injected initially into the reactor to start it. So the neutron will be absorbed by a uranium-235 nucleus. The absorption of the neutron makes that nucleus unstable, catastrophically so, and it will split. And it will always split into two, usually unequally sized, but only ever two daughter nuclei. And often in revision guides and textbooks, it's krypton and barium because that's the most common thing it will split into. That splitting also releases more neutrons, which can then go on to cause more fission because they will then be absorbed by different uranium-235 nuclei. If you control the rate of the reaction, so you may have heard of R values, certainly with the coronavirus pandemic, you've heard of R values. Well, that's a multiplication value. For a nuclear reactor, the reactor is running at the correct level with the R value. The replication or multiplication factor is 1. So every neutron goes on to make cause a further an additional fission. If they are not controlled, if there's allowed to just 2 or 3 go on to create 2 or 3 fissions, then another 2 or 3 fissions, or another 2 or 3 fissions, you end up with an exponential growth, and that basically is uncontrolled and would cause a meltdown and an explosion. So the control rods are there to control the rate of reaction. If you want to reduce the rate of reaction, you insert them further into the reactor. If you want to increase the rate of reaction, maybe it's gone down below 1, you would withdraw them slightly from the reactor. So they're very carefully controlled, and they work on the reactor. They're usually top down, so that if they were to fall, they'd fall under gravity and basically turn the reactor off. So the other material within there is the moderator. Now the moderator is needed to slow the neutrons down, because the neutrons, when they're first released, they're going too fast to be absorbed. So the moderator is made from a material, a substance which will slow them down and allow them to be more easily captured by uranium nuclei.